So in this video we're going to have fun with vectors. We're actually going to do something quite advanced in mathematics. We're going to prove a geometric theorem. We're going to keep it pretty simple, very basic geometric ideas, but nevertheless we're going to move into the meat and drink of mathematics, which is algebraic proof. Now what do I mean? Well, if I draw a triangle, any triangle like this, so we're not going to actually measure its sides because we're going to work algebraically. If we work algebraically and make general statements, then we're going to have proved the result for any triangle rather than this particular one. Now I'm going to draw a line across here which is from the midpoint of one of these sides, so let's choose this one, to the midpoint of this side, so from here to here. And that's because there's a theorem that I want to try and prove, which I'm going to show you on a little piece of paper. So the theorem looks like this. It says the length of a line connecting the midpoints of two sides of any triangle, so this length here, is, according to this theorem, exactly half the length of the other side. And looking at the diagram, that looks to be true, but can we prove it? Well, we're going to give it a go. What the aim of this video is to give you some confidence in being able to do something like this. It seems sort of quite advanced and mathematical, but actually once you try on very simple examples like this, pause the video obviously when you feel confident and give it a go yourself and then see if that's the right answer. But hopefully after a while you'll feel confident to do a fairly advanced thing, and you'll get there fairly rapidly. The first thing though is to build your confidence. So how do we do it? Okay, how do we actually prove something like this, that this length is half of this? Not just show it or think it, but prove it. Well, the answer is we think in terms of vectors. Now, let's just label our diagram here. So if I go A, B, C, and our midpoints, let's say M and N, that starts us off. That gives us a vocabulary to work with. According to our theorem, Mn is half of BC, right? So I'm going to write that down because that's the thing we want to prove. Okay, we want to prove that Mn is half of BC. Okay, so simple so far, yes? Let's go ahead and do it then. Well, what I'm going to do straight away is say, think about overlaying vectors onto your diagram. So Mn was a length, or is a distance between these 2 points, M and N. If I overlay a vector onto here, well, then I've not only got the distance, I've also got direction. So I've got length, or magnitude, and direction. And it's that property of vectors that's really helpful here. Anyway, let's just then think of the direction. Well, direction either goes in that direction from N to M, or in this direction from M to N. And if I put a line over the top, then I've turned that distance into a displacement vector, if you like, a displacement vector from M to N, the displacement from N to N. Displacement is not just the distance between M and N, it's in what direction as well as how far have we got a displacement from M to N. Okay, so I've got M to N, and I'm going to draw in my diagram an arrow. So now I've got a vector overlaying my original diagram. I'm going to do the same with BC. So BC becomes B2C. Okay, and here then I just notate that with an arrow over the top. So now the triangle theorem that we use to do these proofs says that if we think about displacement, that to get from here to here, the Mn is going to be exactly the same as Ma plus An. This is the triangle theorem, the triangle law rather, of vector analysis. So what I can do now is define two more vectors. Okay. So let's say I've got vector A here, which is MA. So I'm going to write that down. MA, like that. So from the M to A, so the M to A direction is defined now as vector A. Any vector, so obviously these would be two numbers, you can think of it as a column vector, but we're just working algebraically, so we're not actually putting the numbers in, we're just giving it the title A, so it's just vector A. Okay, so now A to N, we're going to call B. So we don't know what that is. We do know it's probably different to A, so we don't know that they're equal. So we're going to go A to N and again indicate the direction on our diagram. Okay, now what's M to N in terms of these vectors here? Well, M to N, let's write it here, equals A plus B. Written that down, have we? Let's write B on our diagram there. Okay, so equals A plus B. Now we've got to look at the relationship between MN and BC. So the next thing we're going to look at is BC then. And to get from B to C, we can go around the houses. So B to A to B. So we need a vector or an expression for BA. So let's write BA. Okay, well BA must be two of these A's because this is a midpoint here. So we're given that this is halfway. So this length must equal this length. Sometimes on the diagrams you see those marked with a dash like that. So this length equals this length. And if the length's the same and the direction's the same, we say they're collinear, then this vector here, which is B to M, that must also be A. Okay? So B to A, which is what we're looking for, equals 2A. And similarly, what we want now is A to C to get us to the tip of this vector here. So we've got A to C is going to be 2B, okay, because this is going to be B here. So 2B. So we've got B to C, which has to equal B to A, like this, plus A to C. And you can see this is B to A to C. You can see then it's B to C. You can almost cover up these two A's, and you can just see that it's from tail to tip. This is the tail, this is the tip. So BC is obviously B to A plus A to C. Okay. So we've got B to A, which is 2A. We've got A to C, which is 2B. So we're now ready, if you like, this is the final stage, to look at the relationship between these two. And the way to think about this maybe is we can factorize this algebraic expression here. Okay, so if I factorize, pull out the 2 then, put the A plus B in brackets, it becomes obvious that therefore Mn equals, so A plus B equals half of BC. Which is, just as a quick check, which is exactly what we were asked to prove. Okay, so there we are. That's what was shown. In the old days they used to write QED. Let's write that here, why not? QED, which was to be shown or demonstrated. So let's do another one. If I draw a trapezium this time, what I'm going to do is draw a midpoint to midpoint, a central line here, so it travels down from there to there. And let's have a look at the theorem. So this theorem says that in any trapezium ABCD, the length of MN, which connects the midpoints of the parallel sides AB and CD, must be half the sum of AC and BD. Well, okay, so it's all in terms now of letters. So let's put the letters on. So we've got the vertices A and B. So these are the parallel sides that it refers to, and C and D. And the midpoint MN. So M is the first midpoint and N is the second. Okay, so it must go like that. And what does the theorem say? The length of MN, so this central line here, connects the midpoints of the parallel sides AB, CD, so AB, CD, so that's right. So in other words, these are, that must be equal to that, and that must be equal to that. Okay. Must be, apparently, this line must be half the sum of AC and BD. So it's these two outsides. So AC and BD added together gives us twice the length of MN. Okay, that's a way of thinking about it. So let's get rid of the theorem and write that down as the thing that we've got to prove. So we've got to prove that, let's put it this way, AC plus BD equals 2MN. And to prove that, we simply vectorize the whole thing. So we add vectors to our diagram, and if it works for vectors, then it will work for the lengths as well. Okay, so the very first thing we've got to do is look at A to C plus B to D. And we might as well look at them together. So I'll write them down together and add some vectors now. So A to C, well, we're going to go then in this direction. M to N, so that's going to go in this direction, and B to D. Now, if I think about going from A to C in a circuitous way, going around the houses a bit, let's just erase now these equal signs. So that is equal to that, that is equal to that, okay. Then I'm going to go along in this direction here, really no alternative, and go down this middle line here. So then I'll end up going along from N to C, and I'll end up at the tip of my A to C vector. So if I define this as A, this one opposite here, let's call that B. And then we need this length here, which we'll call C. Okay, so that means that AC, A to C, is going to be equal to A plus B plus C, because A plus C plus B must be the same as A plus B plus C. We can commute. So commuting vectors, perfectly okay. So A plus B plus C. Keep it nice and straightforward like that. Okay, so that looks like a G. Let's just erase that, make it a bit clearer. Okay, so C. Right, now What we've got next then is B to D. Well, if I'm going from B to D a roundabout way, I'm going to go in this direction. So we'll define a B to M vector. We've already got our C vector, and we're going along from M to D. So that's in this direction here. So from B to M, well, that's going to be the same magnitude as A, but in the opposite direction. So it's reversing A. In other words, it's going to be negative A. It's going to be positive C, and then negative B. Okay, because again, these two arrows are pointing in the opposite direction. Okay, so we're going to write minus A for this one, plus C, minus B. And what we can do immediately then is just cancel our A plus B plus, this is supposed to be C, isn't it? So cancel our A's. I still didn't write that very well, so never mind. A plus B, now our B and our minus B is going to cancel like our A and our minus C, and we're just left with, there we go, so I can just circle that so you can see that. There's a positive C there, and there's another positive C there. So we're nearly done. A little bit of cancelling there. Some very straightforward algebra. And what we've shown is that A to C plus B to D is equal to 2C. Well, C is M to N, so equals 2Mn. Therefore, A to C, or AC rather, plus the length BD must equal 2Mn. We don't need the vector notation there. And that, as Euclid would have said, was precisely what we were required. What we were required to prove. So, QED. One more then, and I'm going to draw now a quadrilateral. And what I want to do is join the midpoints, because I want to prove this theorem. The sides whose vertices connect the midpoints of all four of these sides, so the sides whose vertices connect the midpoint. So in other words, if I draw it across from here, and let's get down to this midpoint here, so join all the midpoints together, and this one here. Okay, so the sides whose vertices connect the midpoints of any quadrilateral, so that's the outside figure here, will always form the inside figure, which is a parallelogram. So any quadrilateral, and you'll always get a quadrilateral, you'll always get a parallelogram, I should say, in the middle. Interesting, but can we prove it? Well, all we've got to do, if you think about it in terms of vectors, is prove that if I define a vector across from this midpoint Mn, must be the same, exactly equal to this vector here. Let's call it PQ. Because any vectors that are equal must always be parallel to one another. Okay? So, all I've got to do to prove this one is prove that Mn, M to N, is equal to PQ. Okay, how am I going to do that? Well, again, you don't want to go along these obvious directions. You want to go around the houses. So I'm going to define the outsides, my quadrilateral, in other words. So if I think about M to N, for example, let's have this as being vector A, and this will be a different length, so we call this vector B. So M to N is A to B. So M to N is A plus b, I should say, a plus b. Okay. Okay, what about PQ? Well, if I want to work out PQ, that's going to be a little bit more elaborate. I need to label my sides, because what I want to do is go right round the outside edge. So A, B, another B. Okay, so we just have that going in the same direction, so that's another B. This one here would be C. Okay, so C. And this one here would be A. And what I'm going to do is label this D while I'm at it. So just going along here. And now I'm ready to have a look at P. Whoops, to have a look at P to Q. Okay, now P to Q. Obviously, I could just say is D plus D minus, I should say, D minus C. So I could go in that direction here. What I actually want to do is go all the way around the edges. So I take in all these A's and B's as well. And the other thing I want to do is get rid of the A to B's a little bit. So let's think of it like this. Let's complete this for the moment. So D minus C. Okay, so to get rid of my D's, if I think of my two A's here as being an alternative direction, so okay, now let's just label the vertices to start with. I didn't realize I hadn't done that. Okay, so I've got A, B, C, D. It's getting a bit messy now, but it just helps to have those vertices labels. Right, now if I'm going to go along from D to C then, okay, then another way of getting from D to C, so another displacement vector, is I want to add these three displacement vectors out the outside. In fact, there's six, because there's two A's, two B's, and two C's. So in other words, D to C, which is 2D, has to be equal to two of these A's, so going around the outside now, two of these B's, and two of these C's. Okay, now one thing you can do with vectors is you can divide through, so you can multiply, you can sort of factorize, but we're going to actually divide through now by 2, so to get rid of all these 2's. So if 2D equals 2A plus 2B plus 2C, then D must equal A plus B plus C. Like that. And that's a really useful finding, because if I'm going to think about PQ now in a slightly different way, let's go round the outside. Okay, so P to Q, then I can go along here, which will be negative D, but I now know that D is A plus B plus C. So P to Q, if I start my journey going around the outside, is going to be equal to minus D, so that'd be minus all of this. So it'd be minus A, minus B, minus C, and now plus 2A. So we're up to the A vertex, up to here, so plus 2A. Now we're going to go down from A to B, so plus 2B. And now I've only got to go halfway across here, so from B to Q, so it's going to be positive, so plus C. Now, that long string looks pretty horrendous, but what you'll be able to see quite quickly, I hope, is that it's very simple algebra. We just cancel now. So I've got, well, all I can cancel actually are my C's. So if I cancel my C's first to get rid of those, so minus C plus C is going to be the 0 vector, so those disappear. And I'm left with minus A plus 2A. So let's just circle that so you can see it very clearly. Minus A plus 2A. So now let's write this down. So 2a minus a, in other words. So 2a minus a is going to be, well, just a. Okay. Now I've got minus b, I won't highlight it, just minus b plus 2b, well, 2b minus b then, so 2b minus b is just plus b. And that is all that I require to prove what I set out to prove, because mn we've already said is a plus b up here. Let's use it. No, that's okay. Let's just tick it like that. Okay, m to n is a plus b, therefore m to n must equal p to q. Which was exactly what we set out to prove. Good. So, lastly, I'm going to work through this in a different kind of way very quickly, just to show you that, you know, if you looked at the way I proved something and then tried to memorize that and try to copy that, then that wouldn't really be doing what you need to be doing, which is gaining the confidence that you can do this for yourself and think it through and get the right answer. So we now have this tool of vectors that we can work with. Pity poor Euclid over here who didn't have this, and all his followers right up until the mid-19th century. Now that we've got vectors, fairly easy to do, you just need to practice it. You can use the same models as I've shown you just there, but try putting the arrows in a different way and try different ideas and see if you can still prove it, but prove it your way. Now, one final idea that I want to give you though is sometimes when you get something like this, you actually want to invent a new vector. You don't necessarily want to always use the lines that they've given you. So this is just an extra idea. It might not be useful, but it's an interesting alternative way of proving this same theorem. So we need to prove that mn is equal to pq, just as before. Mn is equal to pq. And that will prove that this is indeed a parallelogram. And I've just written down as well that we have this finding that D is equal to A plus B plus C, because that's going to be very useful. Okay, now the very first thing that we want to look at, just as before, is what is the vector mn? How do we get from n to n? But this time what I'm going to do is I'm going to suggest, well, we could go A plus B, but I'm going to go kind of backwards, and rather than going all the way around the houses, I'm going to draw now, okay, I'm going to draw a vector going from D to B. So I'm going to draw a vector going right across here, okay, and if I'm looking then at, let me see, what way do I want to do it? If I want to go down here and across there this time, so take a shortcut, I'm going to define it as pointing in that direction. Like I say, that's arbitrary. It could have been pointing in the other direction, would have worked just as well. But let's just point it in that direction and see how it works out. So instead of going up A plus B, I'm going to go down. So it's going to be negative A. Positive, well, I need a new vector here, so I'm going to call that E. So positive E. And we're negatively along here to get back to get to our tip. From B to N is going to be minus B. Okay. Now, if I think about PQ, what have I got? I've got a very similar kind of thing. A similar route now has opened up. I've got this minus D. Okay. Again, positive E. So positive E. And now positive C. So plus C. But I know that PQ, I know that D is a plus b plus c. Okay, a plus b plus c. So minus d, negative d, must be negative a, negative b, negative c, plus e, plus e, plus c. Okay, so all I did was sub in, we could call this 1. And sometimes it's good actually to put a little note for the examiner. So all I did was sub in 1 right there. And now I can do a little bit of cancelling. So I've got minus a, well that can't cancel, minus b can't cancel, but the c's can cancel. So minus c plus c. And hopefully you can now see that we've proved, in a slightly different way, we've proved our theorem. So mn equals minus a plus e minus b, and pq also now equals minus a plus e, so just commuting this, changing the order, plus e, and then minus b. Therefore, mn equals pq, and I'm just going to write therefore mn what have we got? MNP, let's write it MNQ, go clockwise. MNQP is a parallelogram. There we go.